All right, class, we're going to get started. All right, so where is everyone today? What's going on today? Okay. Thank you all for being here. Thank you all, everyone who's here. Thank you all for being here. I was just curious why the numbers are lower than usual this morning. Okay, so today we have a couple of announcements. So today we're going to be covering turbulent boundary layers, including some videos towards the end of the lecture, covering some of the material that we'll have discussed today and setting us up for the next section. As a reminder, I'm at ASCHE next week. So Monday, Professor Whitty will be giving you an introduction to Aspen and basically showing you how you can use Aspen to solve some pipe problems. On Wednesday, Rob, your TA, is going to be talking about drag on solid objects. We're going to set that up today, and then Rob is going to continue with that on Wednesday. Finally, for announcements, you should see that the CFD project groups have been assigned. This is the Google Doc or Google Sheet that I sent out in an announcement with the CFD project groups. I also posted an updated tutorial PDF on Wednesday with instructions for what you have to do on the first one. Part 1 is due next Wednesday. Yes. The tutorial PDF is actually in files, or is that under the? It's in files. It's in files. Okay. Yeah, it is in files. And one thing I should note, I mean, all the groups, I'm aware that I'm asking all the groups to do the same thing. So you're all turning in a solution to the same problem. There's randomness in CFD solutions. So no two solutions are exactly identical. Yeah, any pair of solutions for this thing will not be identical. And I'm also asking you for your project files. Yes.
With that note, out of curiosity, what kind of range of randomness is there? Should they be similar or not? Look about the same?
Yeah, they'll look about the same. They'll look about the same, but they will be slightly different. Yeah. One submission per group. Yep. So on Canvas, I set up the groups that are in this spreadsheet are also set up as groups on Canvas, and this is set as a group assignment. So on Canvas, you should have just the option of submitting one per group, and then it'll show up for everyone in the group. Okay. Any other questions on this? Yes. Yeah, the idea is that you all go through it together as a group and you submit one. So one of the constraints here, and the reason why my target was an average group size of about 4, is that we don't have that many licenses to ANSYS Fluent to let everyone just do it all themselves. So you'll notice that you have to sign in to GradPool on the connect.chemeng.utah.edu. So this is not installed on the undergrad pool. It's installed on the grad pool. It uses the GPU for acceleration of the calculations, and that's only on the grad clusters, but we only have 2 of those clusters, and we don't have enough seats for ANSYS Fluent for everyone to do this individually, unfortunately. So they are kind of largest groups, and I do expect you to work together. Okay. On part 2, that will be more, there's many more elements of part 2, including a little bit of lit review and analysis. But for part 1, I do expect you to work together. Yep.
So when we're running the calculations, I feel like I remember you talking about how the CFD can take a while to actually output calculations. About how long should you expect that?
For this tutorial, it should be pretty quick.
Okay.
For the so you'll see for part 2, I haven't yet assigned the projects because the projects are based on a web resource, and that web resource has changed a little bit since last year. So I need to go through it all and make sure it's all okay for you. All the projects are okay. But some of the projects do take a little bit longer, require more computational time than others. Let me get back to you on that. Talk to other groups. Yeah. But I mean, that's not unreasonable for a CFD, right? So some CFD calculations, we'll actually look at the results of some in our videos today. We're going to see some CFD calculations from what's called direct numerical simulation. So this is where we try to simulate turbulence without making any approximations, without using the Reynolds average Navier-Stokes equations, where we directly compute the Navier-Stokes equations. And those are simulations that can take days or longer on supercomputers. So in the world of CFD, hours is not very long. Okay. Any other questions? Okay. And then just quick follow-up. I don't see him here. I didn't answer this question of what zeta was. So there was a question of, what is zeta, dimensionless distance from the wall? And actually from what was given on that slide, we could have answered that question. So we said that theta 99, right, the boundary layer thickness defined as the point where the velocity is 99% of the way to free stream, was 5 over square root of REX. So that corresponds to this here. That's where the velocity is 99% of the way towards the free stream velocity. And from that, we can see that zeta is y times square root of u over nu x, is what this dimensionless distance from the wall is. I don't expect you to know or have that memorized, but I just wanted to follow up. Okay, any questions on material or anything before we get started today? So as I said, we're gonna do videos at the end. After we've had a chance to talk about turbulent boundary layers just a little bit more, just so we can make sense of what we're going to see in those videos. There we go. Okay, so we were talking about the transition from laminar to turbulent flow last time. Roughly what Reynolds number do we see this transition from laminar to turbulent flow in external flow? Yeah, I hear numbers 10 to the 5th, also up to 10 to the 6th. So anywhere in that range, 10 to the 5th, 10 to the 6th, we're going to call transitional regime, right? So that's where we see transition from laminar to turbulent flow. But this behavior, turbulence, is the result of a nonlinear instability, meaning that very, very small perturbations can give rise to turbulence at a lower Reynolds number, at an earlier point than you would get it otherwise. So turbulence is very sensitive to initial conditions. Small changes can cause the transition to happen earlier. So we discussed this in internal flow, right? When we talked about the Reynolds experiment, the apparatus that still exists today. And when Reynolds ran his experiment, he saw a higher transitional Reynolds number than you would see today because of the influence of traffic and other noise kind of shaking the building, shaking the experimental apparatus. Very, very small amount. Those small perturbations cause the transition to turbulence to happen earlier in that internal flow experiment. We see the same thing in external flow. Very small changes can cause transition to turbulence to happen sooner. So, for example, this is a flow over a flat plate we've been talking about. Reynolds number based on length of 100,000, so 10 to the 5th. So this is just at the start of what we would call the transitional region. And you can see these waves forming, indicating that there's something unstable happening here, but it's not really fully tripping to turbulence. Maybe by the very end of the plate, we can start to see some more characteristics of transition. But here we can see that this plate is now adjusted to an angle of attack of 1 degree, right? Very, very small amount. And at the same Reynolds number based on length, and we can see a fully turbulent flow by the time we get to the end of the plate, okay? So very, very small changes in initial condition can give rise to an earlier onset of turbulence. But sometimes this is actually going to be useful, and we'll look at some videos illustrating this, but first we have to understand some more concepts. For example, in flow around a golf ball, this is kind of the classic case where if we look at, so this is an image from your text. We're visualizing a cannonball being dropped into water. From the same height, the cannonball is coming to the same speed before it hits the water in both cases, both the left and right photo. It's the same size and mass. The only difference is that this one is smooth and this one is rough. Okay, it's the only difference between these two cases. And you can see that there's a substantial difference between these two, right? And what you're actually observing here is that in the smooth case, this is the point where the boundary layer is separating from the sphere. Basically, this is the point where, because of the curvature of the surface of the sphere, the flow is basically no longer able to follow around that curve. And from here on, our boundary layer theory falls apart, and we're creating what's called a wake behind this object. And we can see that in the rough sphere, that the point where the boundary layer separates and where we start to create a wake behind the sphere is further back, right, on the sphere. What this tells us is that this roughness has caused this boundary layer to transition to turbulence earlier. So it's become a turbulent boundary layer. Because one feature of turbulent boundary layers that we're going to discuss is that they stay attached for longer. So they delay separation. And that can have some pretty dramatic effect. So if we look at this is coefficient of drag versus Reynolds number for a sphere, either a smooth sphere or a rough sphere. And you can see that, let's say we're sitting here at Reynolds number of about 10 to the fifth, right? So just the onset of transition. So this is a point where the flow is incredibly sensitive to initial conditions, right? Where just a small perturbation can cause the flow to trip from laminar to turbulent, right? From laminar to turbulent. And what we can see is that with a rough sphere, so if we just roughen up the sphere a little bit, make the surface of the sphere a little bit rougher, then we drop from this solid curve to this dashed curve, and there's a pretty large difference, pretty substantial difference in drag coefficient if we do that. Okay, we're going to talk about why this occurs, but turbulent boundary layers, the main concept here is that small perturbations can give rise to an earlier onset of transition to turbulence. Okay, so here we have a plate at a very, very small angle, and we see a change in the characteristic of the flow. And here, all we've done is just roughen up the surface of the sphere a little bit, and we see a dramatic change in the behavior of the system. Okay. So for example, on the final exam, I'm going to ask you one question. So in addition to a true/false question, there's going to be a question where I give you different flow scenarios, and I ask you, is it laminar, transitional, or turbulent? Okay. And up till now, we've mainly been talking about laminar or turbulent, but now this transitional regime is really important, and that's because in this transitional regime, you can get wildly different kinds of behaviors, right, depending on exactly what your initial conditions were. And so you have to just tread a little carefully around this transitional regime and know when to identify it. Okay. And so for external flow, we'll define as a Reynolds number based on like about 100,000 to a million. 10 to the fifth to 10 to the sixth would be our transitional regime. So I want to talk about boundary layer separation, right? We're going to go into some semi-empirical theory to describe what the velocity profile in a turbulent boundary layer looks like. But before that, I just want to talk qualitatively about like, why do golf balls have dimples? And we'll see some video demonstrations of this at the end of today's class. But the answer is that the turbulent boundary layer stays attached better. So we alluded to this on a previous slide in terms of the shape factor. So turbulent boundary layers have a smaller shape factor than a laminar boundary layer. Smaller shape factor indicates that they are less likely to separate. That's not really that satisfying. But one way to understand this is that turbulence causes mixing, right? Remember, we defined this as, in the last chapter, we defined turbulence in terms of its ability to mix things, right? So turbulence drives mixing, and this mixing of the turbulent boundary layer actually mixes momentum, right? So it's easy to think of turbulence mixing like the, if we have some smoke or something, or you pour milk into a cup of tea, turbulence helps mix that material together, right? But turbulence also causes mixing of momentum. So it takes fluid that's moving fast and it mixes it into regions where the other fluid is moving more slowly, and vice versa. So turbulence also mixes momentum. And so one effect of this is that it brings in momentum from the high velocity free stream closer to the surface. And if we bring the free stream closer to the surface, that means we have a thinner boundary layer, and this tends to reduce the wake. By mixing in momentum from the free stream, we tend to reduce the wake. So here is flow over around, for example, this could be the top of a cylinder or the top of a sphere we're visualizing. Then we're visualizing the boundary layers we go over. And in laminar flow, with a laminar boundary layer, we get pretty early separation. But with turbulent flow, we end up with that boundary layer trying to stay attached to the surface just a little bit longer. And that has the effect of reducing the wake. We saw a similar thing gave rise to the difference in velocity profiles within a pipe. Right, in laminar flow, we have separate lamina or layers of fluid that are basically flowing past one another, and not efficiently mixing with one another. So the only transfer of momentum, so to think of this in terms of momentum transfer, the only transfer of momentum in the laminar flow profile was through these layers kind of sliding on top of one another. And the layer on bottom, so if we're looking near this wall, the layer on the bottom traveling a little slower than the layer on top. And so it's slowing down, it's transferring some momentum from the high speed fluid to the low speed fluid through just that shear between those layers. And so we get this nice smooth parabolic velocity profile. In contrast, in turbulent flow, we have this enhanced mixing. And so the high momentum fluid that we have in the center of this pipe efficiently mixes momentum and keeps all the fluid at the center of the pipe at close to the same velocity. And so we end up with this relatively flat velocity profile in turbulent flow in a pipe. So the same phenomenon of turbulence, mixing, right? So important key concept here is that turbulence enhances mixing and momentum can be mixed as well, right? We saw it in internal flow and it plays a big role in external flow as well. So turbulence enhances mixing and momentum can be mixed as well. But to use this, right, to use what we know about turbulence, we need to know a velocity profile. Remember, if we came back to our discussion of coefficient of drag, we said that we wanted to approximate the velocity profile in order to solve for coefficient of drag on a flat plate with a turbulent boundary layer. The Blausius solution gives us the velocity profile on a laminar boundary layer, but we need something for the turbulent boundary layer as well. So what you can see from this diagram in your text is that a turbulent boundary layer and a laminar boundary layer, this is plotting velocity versus distance away from the wall. And the turbulent boundary layer is very different, right? But we need a way to approximate this shape. So here, again, as for internal flow, in the turbulent boundary layer, we don't have an exact solution. So we're gonna have to turn to a little bit of analysis plus a little bit of experiment. So we can use an empirical fit to the flow, what's called the law of the wall. We saw this in chapter 6. This is what we use to develop or approximate the velocity profile for turbulent internal flow in chapter 6. And we can use this to get pretty close. But this equation can be a little bit difficult to integrate, and we're going to try to, like all of our factors, like our momentum integral estimates was in terms of an integral of the velocity profile. And this is a little bit difficult to integrate. So Prandtl suggested this, that U over, so the velocity down the stream normalized by the free stream velocity, capital U, there's turbulent boundary layer, is about y over delta, where delta is the thickness of the boundary layer, to the 1/7 power. And if we look at this, so if we compare kind of, idealized curves from experiments in these solid lines at different Reynolds numbers, 10 to the 5th, 10 to the 6th, 10 to the 7th. And the dashed line here is the 7th root profile from Prandtl. You can see that it works pretty well. So we could do this, right, just like we did in chapter 6, but this is in practice good enough to tell us about the velocity in a turbulent boundary layer. Incidentally, also a little bit easier, right? Then even though we have an exact solution to the laminar boundary layer, exact solution in the form of, remember, a set of ordinary differential equations that we integrate to get what we call the Blasius profile. Here we just have an explicit equation, right? It's a fit and an approximation, but it actually makes it easier to do analysis with the turbulent boundary layer. So using this simplified profile, we can obtain, we can go through and develop all of our, look at all of the equations. We can evaluate all of the expressions that we did for the laminar profile and develop expressions for all the parameters that we care about for the boundary layer over a flat plate, turbulent boundary layer over a flat plate. So we'll say delta over x, approximately 0.16. Sorry. Over the 1/7 power of the Reynolds number based on x. This tells us how the boundary layer grows with x. What's that? I'm okay. I'll be okay here. Thank you. The skin friction coefficient we can solve for as well. Remember, what is skin friction coefficient? Anyone remember what this is? You say it for me, maybe I won't cough. What is CF? It's function of x, right? That's a little weird. So why would it be a function of x? Did I have a volunteer? Nope, Paula, yeah. So this is, so it is about the drag that's parallel to the surface, right? And this is telling us the amount of drag per unit length, actually per unit area, that is being felt at a given location on the plate. So most of the time when let's say we have flow over this table, and I'm going to measure the drag because of the flow over this table, right? I would set the whole thing up and I would measure the whole force, right? I would measure the whole drag force on this. And then I would end up estimating the coefficient of drag, which would be uppercase C D, right? But with a boundary layer flow like this, the flow changes as we move downstream, right? Because the boundary layer is growing, right? In this case, we'd see the boundary layer initially laminar and then transition to turbulence. This table's a little rough, so we'd get that transition probably pretty early, right? The drag that we get on a little square of this table, right? The drag that we get on a little square here on this table is different than the drag that we get on a little square here on this table, right? Because the boundary layer is different. right, as we move downstream. That's captured here. Okay, so the skin friction coefficient is like what the local drag is, the drag on like one little tiny piece of the plate. Okay, that's what's described by the skin friction coefficient. And it's a function of x, right? It's a function of the distance down the distance away from the leading edge of the plate or table. So we can take this and integrate it from x is 0 to x is L and arrive at an expression for the coefficient of drag, 0.31 over Reynolds number over 1/7 power of Reynolds number based on length. Okay. And then using this coefficient of drag and the, for example, the fluid properties, the size of the plate, we could then find the overall drag force that the plate is experiencing. Okay. So sort of point your attention now to this. We're not going to use this nearly as much. We'll see when we're dealing with external flow. We have to. So up till now, we've been talking a little bit about wake when we're talking about what happens around golf balls, but we can't ignore that in general when we're talking about external flow. But if we were considering just a flat plate, this is kind of like a Moody chart for flow over a flat plate. So again, we have non-dimensional parameter, which in this case is CD, the coefficient of drag, plotted as a function of Reynolds number. And this is Reynolds number based on length. We can see we have one curve here for laminar flow over a flat plate, right? This comes from the Blasius exact solution. And then we have some curves here. So for example, this curve is what we just discussed, describing the coefficient of drag for turbulent boundary layer over a smooth flat plate. Right, we end up with this curve here. One feature of turbulent flow is that we cannot totally avoid transition. Sometimes we're going to end up with a plate that is just the wrong length or a speed that is just the wrong speed, such that we're in the transitional turbulence, the regime of transition to turbulence, denoted by this big blob here, right? And notice that the onset of it is, a little bit amorphous. And so within the regime where transition to turbulence is important for flow over this flat plate, we have some approximations to what the coefficient of drag would look like. That kind of blend the character of the laminar and turbulent flow solutions with different values of the coefficients in this expression, depending on whether you have kind of standard transition. So if your transition is at 5 times 10 to the 5th, you use this. If your transition is at about 3 times 10 to the 6th, again, that's like perfectly mirror smooth at exactly 0 degrees angle of attack with no disturbances whatsoever, then you would use this form, right? So we see there's basically a range of curve fits that we have to use if we're in the transitional, or if we're close to the transitional turbulence regime. So if we're in this area here. The other thing that you might notice here is that on this CD plot, we have roughness again. So these things here, these different curves in the turbulent regime, these are for different values of, now this is represented as L over epsilon, or the length over the roughness, the inverse of what we showed for internal flow. But for different values of that L over epsilon, we can see, again, different curves, just like we had for internal flow with the Moody chart. And what we can see is that, again, there's a fully rough regime where all of these lines are horizontal, and the in this fully rough regime, the drag coefficient no longer depends on the Reynolds number based on length. So these are some approximations for what those coefficients look like. The skin friction coefficient, right? Again, remember that's like the local drag on a little square of a flat plate, and the overall drag coefficient would be the overall drag coefficient for a whole flat plate of length L. We can see what those look like based on, again, curve fits to experimental data. I know we're going a little bit faster here than we did on the Moody chart because it's more or less the same ideas, just applied to drag force over a flat plate. And we can see that these expressions are independent of Reynolds number, again, just like pipe flow, right? So just like pipe flow, these lines become straight flat lines independent of Reynolds number. So one consequence of this, which we're going to look at when we start talking about drag force on more complex objects, we're going to be using this expression quite a bit. So drag force 1/2 rho CD U squared A. This is going to be the one of the major equations. We've introduced this a couple classes ago. This is going to be one of the major things that we're using in this chapter. We've been doing all of this work to derive CD for a flat plate, right? Which we can look up on this chart or use the relations that we've been plotting. And what we can see here is that there is, when we're in this high or this fully rough regime, there's no dependence of the coefficient of drag on Reynolds number, meaning that there's no dependence on viscosity. And so we've been talking a lot about viscosity and viscous drag and viscous influence of boundary layer. But over a wide range of operating conditions, even just for a flat plate, and we'll see the same thing is true for more complex objects, the coefficient of drag is actually independent of Reynolds number. As long as we're turbulent, the flow will be independent of Reynolds number. And so we can typically just write out, like, for example, one coefficient of drag, right? So if we have a flat plate with L over epsilon of 2000, right? Like maybe that's what characterizes the table or something. Then as long as we're in the turbulent regime, as long as the Reynolds number based on length is high enough, we'll see that we'll just get one value for coefficient of drag. Okay, so you still have to check Reynolds number to know where you are, right? Are you laminar or turbulent or transitional? But once you know you're turbulent, we can see that this regime of coefficient of drag depending on Reynolds number is actually not that huge. And so generally, once we're turbulent, we're going to say coefficient of drag is one value. Okay, and so just a note here, A, when we're talking about flat plates, A would be the plan area. So it would be like the length of this thing times the width. That's why we generally have like L times little b appearing when we're talking about flat plates. The length times the width. That's going to be different for other types of objects, okay? The area will be different for other types of objects. Okay, any questions on that? I want to go to some videos that illustrate some of the things that we've been talking about today. Yes. My guess would just be happenstance of history. Like the people working on this preferred it that way, would be my guess. Yeah. Yeah, some stylistic choice. I don't quite understand. What's that? Yeah, something like that. Yeah. Okay, so we're going to start with. So we're actually going to look at a couple of direct numerical simulations in the videos today. Now, again, remember we talked about modeling turbulent flow in last chapter, and the we said that one reason why we model turbulent flow. One second, make sure I get the sound working. One reason why we model turbulent flow is that we don't have an exact solution to the turbulent flow equations, and even solving them numerically is, or sorry, to the Navier-Stokes equations for turbulent flow, we don't have an exact solution. And even solving the Navier-Stokes equations for turbulent flow numerically is incredibly challenging. It's incredibly challenging computationally. And so typically, for example, in your CFD projects, part 2 and part 1, you'll be using turbulence models to model the effects of turbulence flow. You'll be using the RANS equations and some kind of turbulence model to approximate the impact of turbulence on the mean flow. But we don't have to do that. Like in theory, we know that the Navier-Stokes equations still hold in turbulent flows, and so we can also just like ignore all that RANS stuff that we talked about last chapter, and just straight up simulate the full Navier-Stokes equations, and that's called direct numerical simulation. It is incredibly computationally intensive. The results that we're going to see from DNS or direct numerical simulation today were done on incredibly powerful, supercomputers, right? So it's not really commercially viable at this stage. But with direct numerical simulation, since we're not approximating anything, we can see the full structure of everything that's going on in the flow. And so it makes for some really nice visualizations to understand the things that we've been discussing so far in class. So we're going to start with this one. So this is going to be a simulation of a flat plate transitioning from laminar. You can kind of see in the background here, laminar to turbulent flow. And it's a simulation of what you might do in a wind tunnel or something, right? I don't believe this one has sound. So they showed the grid, first of all, right? So they showed the grid that they're using to actually do this computation. And now we're visualizing the flow as it encounters a flat plate, right, with this nice smooth point, and starts to flow over the flat plate. And now they've made a point to say that they included free stream turbulence, right, which is the turbulence that's outside of where the boundary layer is, right? So turbulence that it encounters before it even approaches the plate. And we can already see the boundary layer here, right? You see this, the free stream is marked. It's a little wiggly because there's turbulence in the free stream. And then down here, we can see the boundary layer because by the no slip condition, right, we have the velocity going to 0 at the plate surface. And so we can see this getting dragged, right, this marker getting dragged along the surface. You can see how thin that is. So one of the things they're concerned with is the interaction of the free stream turbulence with the boundary layer, focusing on what goes on near the leading edge, but I want to talk about this. So now what they're visualizing are vortical structures or vortices, like rotational flows, right, within the boundary layer. And we can see that like there's a lot going on at the very leading edge. But then we get to this region where it's really pretty calm, right? Indicating that we have a laminar boundary layer. Right? Then we start seeing these kind of streaks of vorticity leading to, we're going to look at all of this in more detail in this animation, but leading to this more complex structure, leading to like crazy vorticity downstream. That's what we're seeing is transition to turbulence, right? So laminar, transitional, turbulent as we move down the plate. We're talking about free stream turbulence intensity. Those streaks indicate that we're starting to transition to turbulence. Now, we talked about turbulent spots last time, right? And how we have these like arrowhead shaped things that grow because of disturbances in the flow, grow or form kind of randomly and then grow as they move downstream. So now we've shifted camera view, so we're actually watching one of those turbulent spots as it moves downstream. And you can see it moving and growing, getting bigger and bigger, merging with adjacent turbulent spots as we transition into full turbulence. Okay, I know they're just like showing off and doing a 3D animation. But that gives us a sense of the, I don't know, maybe a better sense of the characteristic of turbulence that we've been, and in particular the transition to turbulence that we've been discussing, right? And this is for a flat plate boundary layer. But now from here on in the chapter, we're gonna kind of stop talking about flat plates, and we're gonna start talking about more realistic objects, right, that we might encounter. And so I want to start with there we go. 1 second. Because this video is really short. And this is a video demonstration of the laminar and turbulent flow around a ball, around a sphere. So these are at the same Reynolds number, right? So same relative size, velocity, density, viscosity. The difference is that, in fact, they're probably exactly the same sphere and at exactly the same velocity and exactly the same experimental setup. The difference is that in this bottom case, you can just barely kind of see this scratch going around. That's what's called a trip wire. So it's a small like wire, just very, very thin wire that's been wrapped around the sphere. And that creates enough of a disturbance to take the boundary layer and trip it from laminar, where we have inefficient mixing and therefore early separation, to turbulent, where we have more efficient mixing and we have later separation. And you can see that the width of this wake, the size of this wake, is substantially smaller than the size of this wake. Okay. So what's happening here for the drag force, right? So let's just talk about what's happening for drag force. This is going to be important when we see golf ball data. We're going to see that when we have more complex objects, this is going to be a theme of the next piece of this chapter. When we have more complex objects, there are going to be two components of the drag force on those objects. The first is what we call like the shear drag, which is basically like the drag of, you have high speed flow moving over low speed flow or zero speed flow. And so you're actually having to you have some shear force to actually drag that fluid, right, from like over at high speed over the plate where there's no slip condition. That's what dominates here, right? That's what's driving the drag over a flat plate. And that's what's driving the drag where we have this attached boundary layer. But in more complex objects like a sphere, there's another component to drag, and it can be incredibly important. For a sphere, it's a dominant effect. And that's called the wake drag. So if we look at the flow, if we look at the pressure over this object, we'll see that the flow coming in, right, it's coming in at the free stream velocity. It decelerates to nearly zero at the leading edge, right at the front of the sphere. And by Bernoulli equation, we know that if the velocity decreases, what happens to the pressure? Velocity goes down, pressure goes up, okay, by Bernoulli. So the pressure here is high. The pressure in the wake is low. So we have a high pressure on the front side caused by the flow decelerating, a low pressure on the back side caused by the wake. So high pressure over this area means a large force going this way. Low pressure over this area means a smaller force coming this way. And the net effect is a drag going backwards. So reducing the wake, reducing the size of the wake, reduces the area, right, over which we have that low pressure. And therefore reduces the drag force. And we saw it can be pretty substantial, right, for a sphere based on data. And we can see that here is being induced by a tripwire, right? So the transition to turbulence here is induced by a tripwire. But in golf balls, we don't have a tripwire. We have dimples. Let's look at that. So this is like a counterpoint. We saw laminar flow is awesome from Smarter Every Day. This is like a counterpoint from Veritasium saying turbulent flow is more awesome than laminar flow. You can watch the full video, but we're just going to watch a short piece.
You can see why there is airflow anyway. But the air is from random regular. This is cool. But you also need to be careful leaving a large weight of low pressure air behind you. That's right.
Okay, so we're going to see what sort of effect we're talking about. So first, I want to look at this. This is a again, a direct numerical simulation, but this is now of flow over a golf ball. Okay, so we're actually going to observe the impact that those dimples have on the boundary layer.
Watch now, within a single dimple, as the air detaches and it shears away, varying with the stream's direction. We see that the cumulative effect of the vortices pulls air down onto this direction.
Stop for a second. This is the disturbance boundary layer. Right? This is how the dimples are creating a disturbance. So that previously laminar boundary layer, where they're creating this small little ripple of vorticity, and that is enough to trip the boundary layer from laminar to turbulent. So that's what the dimples are doing, tripping the boundary layer from laminar to turbulent.
We see that the cumulative effect of the vortices pulls air down onto the ball, delaying energy wasting separation. Go.
So the turbulent boundary layer, more efficient mixing, it pulls that free stream air in, right? Pulls the momentum of that free stream air in, which causes a decrease in pressure weight. All right, so last one, it's just going to be like, what would happen if you actually try this? Like, you went back to a perfectly smooth golf ball, what would actually happen? And so this is a video showing exactly that.
Heel a little bit and let it fly. Let's see what the shot trace movement there. Oh.
So, he does, and I'll let you go through and watch this if you're more interested, but he, well, we're just about out of time, but he's been hitting a number of different golf balls. Green would be normal, so it's a distance away from him, right? And he's getting, most of the time, 230 yards, 240 yards on the drive, far further than I can go, I guess. Then you can see that when he hits the golf ball without dimples, dimpleless, the purple He's only ending up somewhere around 140 yards, right? So it's a huge difference, 100 yards, right? Like near almost a third of his drive is gone, more than that, from having the contact. So a huge impact of on. Well, all right, thank you all. I'll see you at the end of next week. Please be nice to our guest lecturers. You know, Robin. I mean, what are they?